Hello, my name is Daniel Beyer from the LMU Munich in Germany, and I am proud to present JavaSMT 3, an easy, ready-to-use library for interacting with several SMT solvers. Satisfiability Modulo Theory is an active field of research, and in the recent years, SMT solvers rose to great popularity in test case generation, software verification, and interactive theorem proving. Hence, our motivation for the ongoing development of JavaSMT stems from the issues that are presented when interacting with SMT solvers, either via binary solver API or text-based. For example, there exists no standardized binary API for SMT solvers. An improvement of this is the unified textual input-output language SMT-lib2, which can be used by almost all modern SMT solvers. In using SMT-lib2 to communicate with SMT solvers, one would not benefit from features only usable via the binary solver API, such as interpolation, optimization, or unset cores. There are proposals to add those features to the standard in the future, and some SMT solvers already overcome this issue by implementing a solution of their own. But the ramifications of this are that even SMT-lib2 parsers need to be adjusted on a per-solver basis. This issue is reinforced as the results that are handed back by the solver may be slightly different from solver to solver. Using the API to communicate with SMT solvers instead of SMT-lib2 offers you the benefits of features only usable via the binary solver API. Besides the already discussed features that are not usable via SMT-lib2, there are also solver callbacks. They enable you to, for example, cancel a long-running SMT query without potential loss of information, which could occur when forcing the SMT solver process to terminate. But as a result of using the API of a solver directly, it becomes more difficult to switch to another solver, as this would result in potentially extensive rewrites of one software, as the APIs of the solvers differ sometimes extensively. This is further complicated as the solvers may not offer a binary API for the programming language used by a user's application. Additionally, the returned model that most solvers are able to compute, again, is not uniform across all solvers. Nonetheless, one may need to use more than one SMT solver, as not all solvers offer all logics, theories, or features. Hence, JavaSMT offers you a library that simplifies the interaction with SMT solvers not only by a unified API, but several additional features that will be discussed shortly. Moreover, particular solvers may be better suited for some tasks compared to others, which will be illustrated by a study we performed later in the talk. Of course, JavaSMT is not the only project that offers a unified way of interacting with SMT solvers. The most notable example would probably be the already mentioned SMT-lib2 with its textual input-output standard. Multiple projects in several distinct programming languages such as C, Python, and of course Java try to ease the use of SMT solvers with sometimes distinct approaches. Here you can see several projects that aim to offer multiple SMT solvers in one single library. To show the versatility of programming languages, not all related projects are shown here. A more detailed list, including Java and Scala-based projects, can be found in our paper. The table illustrates which project uses the binary API or SMT-lib2 to communicate with a backend solver. As a side note, while JavaSMT does not communicate with the solvers via SMT-lib2, one can of course use SMT-lib2 via the binary API to interact with the solvers in our project. Further, it shows some often used features and their availability per project. For example, PySMT, a Python-based project with a goal of rapid prototyping, uses the binary solver API in a similar way to our project. But it allows its users to manipulate SMT formulas without a backend SMT solver. And further, it enables the user to break down SMT formulas, based purely on Boolean logic, such that they are solvable in an SAT solver or a BDD library. In C or C++, one can, for example, use meta-SMT, SMT-Kit, or SMT-Switch. All three offer solver-agnostic APIs, such that the focus is not on the interaction with the multiple backend SMT solvers, but on a user's application. The libraries SBV and WAT4, with their Haskell-based approaches, provide not only multiple SMT, but also SAT solvers. There are even generic libraries developed in relatively new programming languages, such as RSMT2, which uses Rust. Important is that overall, the development of new libraries offering a unified API for multiple SMT solvers shows that there is an ongoing interest in the community to use multiple solvers easily. But to underline the benefits offered by unifying SMT solver APIs, especially the ones using the binary solver API like JavaSMT, we performed a case study. Summing up all points up until now as to why a standardized library for multiple SMT solvers is useful. The necessity of a unified API for SMT solvers is drawn from the distinct binary solver APIs, the multitude of used operating systems in a user's application and the solvers, the differences of the SMT solvers themselves, as well as lack of support for some features when using a textual input-output language. The implication that it would be beneficial to have multiple SMT solvers at one's disposal to be able to switch to a solver that fulfills all needs that arise from a task is obvious. But the question as to how to choose this solver for an arbitrary task is not. To test these implications and to show that they are correct, we evaluated 7 of our integrated SMT solvers on the same set of tasks. The goal is to show that the choice which solver to choose for a particular problem is not trivial. Or, in other words, that there is not the one solver that solves everything best, but that, depending on the problem set one is trying to solve, switching solvers may be beneficial. We used the software verification framework CPA Checker that uses JavaSMT since inception to evaluate the background SMT solvers. To do this, a subset of the tasks used in the software verification competition was used, totaling over 1,000 tasks. Each one of these was evaluated using 3 well-known SMT-based verification algorithms, namely bounded monochecking, short BMC, K-induction, and predicate abstraction. The tasks represent reachability problems encoded in SMT formulas, which use a wide variety of theories and features. For example, control flow problems, as well as problems for bit vectors that need bit vector support in the underlying solver to reason about bit-precise problems. Heap problems, modeling heap memory verification using the theory of arrays or uninterpreted functions in the solvers, as well as loop problems, which tend to generate large state spaces and therefore large SMT queries. We used a cluster of Intel Xeon E3 1230 CPUs and limited the CPU time to 15 minutes and memory to 15 gigabytes. If you want, you can take a look at our reproduction package that offers a ready-to-go virtual machine with the used CPA checker and JavaSMT version installed and all tasks ready to go. Some notes on our analysis. As not all SMT solvers support every theory or feature, we excluded all solvers from the problems that they cannot solve. Noteworthy examples are Boolector, as it does not support integer theory or formula inspection and manipulation, which is needed in most K-induction tasks, for example. SMT interpol's bit vectors are not efficient enough to be used, and YSys2 does not support the theory of arrays. Hence why heap problems are encoded in uninterpreted functions for it. This makes the heap analysis slightly unsound for YSys2. but the formula size and runtime is comparable to that of an array encoding. It is to note that the verification framework was configured such that it works as precise as possible. This ensures that the underlying SMT solvers receive more challenging problems. Furthermore, we track the CPU time returned by CPA checker for the entire analysis, as the overhead generated by CPA checker and JavaSMT is small compared to the SMT problems which are being solved. Also, the overhead of both is basically constant in all tasks. And finally, crashes, out-of-memory errors, and similar problems are not evaluated as they do not contribute to the performance that we want to compare. In the now shown quantile plot, the CPU time of the solvers is compared for k-induction using bit vectors. It is sorted by the nth fastest results such that the tasks taking the longest are on the right-hand side. Note that this means that just because two solvers behave similar on this plot, they do not have to behave the same on a particular task. But we will go into detail about this in a moment. The overall extension of the plotted lines per solver indicate the amount of solved tasks per solver. You can clearly see that, for example, Boolector in purple extends only to around the 250 solved tasks mark, mainly due to Boolector's lack of support for some solver features needed for k-induction. But still it was competitive until that point. And it's clear to see that MathStat5 in green and YSys2 in a yellowy earthy tone seem to be the contenders for the best solvers in this category of tasks. This quantile plot shows the CPU time for bounded model checking using integers. It has the same structure as the plot before, but you can see some differences in solvers' performance. 4 different solvers seem to perform well. SMT Interpol in purple, for example, starts to take more time earlier than the other 3 well-performing solvers, but therefore performs slightly better in the long run. Overall, the solver's performance started to differ only in non-trivial tasks. However, it may be that a task is easy for one solver but not another. It is to note that while we only show 2 of such plots now, we would see similar differences in solver performance emerge if we would plot out more categories. You can take a look at the reproduction package if you want to see more plots or the raw data. While these plots showed that the overall performance of solvers differ, we could not see details per task. If we now take a look at the comparison of the 7 solvers with our 3 verification techniques split into an integer and a more precise bit vector category, for some tasks in detail, we can see some more interesting distinctions. The ERR in violet stands for errors in the verification. For example, missing support for formula manipulation. Empty cells represent missing theory or feature support, and the orange TO represents timeouts. Note that some verification techniques rely on binary solver API features, such as interpolation. In fact, you see the best results per task. And here we can clearly see that even in the just 10 shown tasks, 5 different solvers perform best, illustrating that the choice of solver matters even more. Here too, if you were to illustrate more tasks like this, one would see a continued trend of different results. To sum up what we just looked at, distinct SMT solvers behave differently on specific tasks. Some are not usable due to the already discussed problems, and the performance of the solvers changes on a per-task basis. This extends to the features needed in the tasks that are not offered by a textual input-output format. And importantly, there is no one single fastest solver observable on a per-task basis, and the choice of which solver to use per task was not answerable before actually solving the task. Now that we have established the need for a unified API that offers multiple SMT solvers that include binary API features, let's take a look at what JavaSMT offers. Java SMT simplifies the usage of SMT solvers by offering a single API for all of them. Additionally, our open source project provides most features usable via binary API and has been designed in such a way that one can seamlessly switch between back-end SMT solvers. Java SMT is type-safe for the theories used and produces only minimal overhead. To illustrate the versatility of Java SMT, let's take a look at the available theories per solver. You can see that with the 8 available solvers, every major theory is represented multiple times. Further, you can see that some solvers have very distinct theories available. Boolector, for example, is specialized in bit vectors and misses integer support. Z3 or CVC4, on the other hand, offer every major SMT theory. And taking a look at the available features, most of which are only usable via the binary API of the solvers, we can see that here too, most options are represented multiple times. Note that we try to keep all solvers as up-to-date as possible. Therefore, changes in the available theories and features occur only when the background solvers either remove a feature, for example, Z3 removed interpolation support a while ago, or when features or theories are added. Let's take a look at how Java SMT works in practice and what you as a user can expect from our project. Here you see a conceptual overview of Java SMT, embedded between a user's application and the available SMT solvers. The main object used to interact with Java SMT is the solver context, located in the upper middle part. It defines the scope and lifetime of all objects created inside of it, and memory used by the SMT solvers inside of a solver context is tracked such that when the solver context is closed, all unused objects are deleted and memory is freed again. To create formulas in various theories, formula managers are provided by the solver context. A formula manager is bound to the theory used, for example, an integer formula manager for integer theory, and allows the type-safe creation and combination of symbols and formulas. As Java SMT supports the visitor pattern, formulas may be structurally analyzed. That means that one can split up formulas into its components and inspect it, or perform various manipulations inside. Examples for this being the substitution of symbols or applying equisatisfiable simplification. A prover environment represents a stack of Boolean formulas, which may be checked for satisfiability. The stack can be used to check Boolean formulas incrementally using push and pop, and even assumptions may be used for a subcheck, as long as the underlying SMT solver supports these features. After a check for satisfiability, the prover environment can return a model, an unset core, or an interpolant for a given query. A formula created by a formula manager can be used and solved in several distinct prover environments. Further, as long as a solver supports it, Java SMT allows concurrent usage of several solver contexts and even multiple prover environments inside a single context. It was mentioned that programming languages can limit the choices of solvers one has. Java SMT overcomes this by using Java native interface wrappers in 6 of its 8 solvers, as only Princess and SMT Interpol are Scala and Java based respectively. Some of these JNI wrappers are developed by the solver developers and some are extended or developed by us. Such is the case for Boolector and YSys2. In the case of MathSat5 or OptiMathSat, we extend present JNI wrappers, for example with exception handling, to serve our needs better. In the new version 3 of our project, you will find 3 additional SMT solvers that were partially mentioned already in Boolector, CVC4, and YSys2. Bool actor, as already mentioned, is specialized in bit vectors and offers good results in theories connected to them. CVC4 boosts the versatility of JavaSMT as it offers all major theories. Moreover, EISIS2 shows good results in general and offers most binary API features. And lastly, Bool actor and soon EISIS2 can be configured with multiple backend SAT solvers such as Minisat or Picosat in JavaSMT. While all solvers present in JavaSMT are available for Unix systems, multiple are now available for Windows, such as MathSat5 or Z3. And to make JavaSMT3 usable on all mainstream operating systems, some solvers are also available for macOS, for example Z3 or SMT Interpol. And lastly, 2 build systems in Ant and Maven are now available in JavaSMT3, simplifying the download and installation of SMT solvers in JavaSMT for all operating systems, and reducing the amount of work needed to integrate JavaSMT into a project. All this improves not only the versatility of JavaSMT, but usability as well. Several examples for the usage of JavaSMT with multiple SMT solvers as well as the build systems are provided on our GitHub page. To sum up what we just heard, we performed a study to show that it is often not sufficient to use only one solver for a particular task and that textual input-output languages may not offer all features needed in said task. In detail, we used the software verification framework CPA Checker to compare 7 SMT solvers with each other in a broad variety of tasks. We exhibited the distinct results achieved by the solvers, and we could clearly see that the compared solvers were not universally usable for all tasks. Further, the SMT solvers' performances differed, such that it became clear that it is beneficial to have multiple solvers at your disposal. Lastly, we showed that the choice which SMT solver is best for a specific task is not trivial, supporting the use case of JavaSMT. Ultimately, we present the improved third generation of our unifying Java API for SMT solvers. The API offered by JavaSMT is stable and easy to use. Our library offers now extended support for additional operating systems, more included SMT solvers, and multiple options for build systems. Moreover, we offer 8 solvers with a multitude of theories and features available. And lastly, our library is still in active development. To give you an impression about this, it is planned to not only update the already existing SMT solvers, but to incorporate even more solvers. Examples for this would be CVC4, as its development moved on to CVC5, and the maintainers' own Java support for CVC4 was dropped for the moment, but is aimed to be replaced in CVC5. For Bool actor, only small fixes are to be expected in the future, as the developers moved on to a successor solver, Bitwurzler, which we aim to integrate into JavaSMT in the future. Another build system in Gradle is being added right now and will be available shortly. Further, there exist plans to offer solver-independent features, for example, Craig interpolation. And besides our ongoing efforts to support more SMT solvers for Windows and macOS, we have plans to support more CPU architectures, like for example the ARM architecture used in Raspberry Pis. JavaSMT is open source and available under the Apache 2 license. Please feel free to visit our GitHub page, which offers instructions and examples for JavaSMT and our build systems. If you're interested in more details about our talk in particular, please feel free to read our paper or take a look at our reproduction package, offering all raw results for our study, as well as a ready-to-go virtual machine to reproduce our results packed with a guide explaining the usage of JavaSMT and CPA Checker. Thank you for your time.